We're going to start with question one. Question one is about chain rule. So with the first derivative, we're asked to compute the derivative using chain rule. And the way that I like to remember it is that f prime of x, I have the derivative of the outside times the inside, so minus sine of e to the x times the derivative with respect to x of the inside, the derivative with respect to x of e to the x. So this is minus sine e to the x times e to the x. Now here, to compute the second derivative, which is part b, it's slightly more challenging. What we have is we have a product rule. So for the second derivative, we need to take this expression and solve its product rule. Now, here, what I'm going to do is I'm going to do a little f prime g plus f g prime. And this is in my head. This is in quotes. And here, f is going to be minus sine e to the x. And g is going to be e to the x. So here, f prime is going to be another chain rule. It's going to be minus cos e to the x times the derivative with respect to x, e to the x. And g prime is going to be the derivative of e to the x, which is simply e to the x. Here, I'm going to finish this off to give me minus cos e to the x times e to the x. Okay, and now for the second derivative, it's f prime g plus f g prime. So it's minus cos e to the x times e to the x times e to the x plus minus sine e to the x times e to the x. And if we'd like, we can simplify it down. So minus cos e to the x, e to the 2x, minus sine e to the x times e to the x. And we're done. In question two, we have an application question. And here it starts about Boyle's law. And Boyle's law is a simplification of Puvner, or the pressure times the volume equals the number of moles times a constant times the temperature. And this is something that you will see a lot in chemistry. This is a classic chemistry question. But Boyle's law, what we have is we have the temperature staying constant. So this nRT becomes a constant term C. And suppose that at a certain instant, the volume is 600 centimeters cubed and the pressure is 150 kilopascals. And the pressure increases at a rate of 20 kilopascals per minute. At which rate is the volume decreasing at this instant? So what we're looking at the change with respect to time of my volume. And in order to get this, I have my expression PV equals C. So I'm going to derive both sides with respect to time to see if I can get this dV by dt term. So here, we're assuming that P and V are both variables of time, and C is constant. So that'll come into play. Now, this means that I have a product rule. So I have dP by dt times V plus P dV by dt equals dC by dt. Now, dC by dt, as this variable here is constant, this is just 0. So now I have that P dV by dt equals minus V dP by dt, or dV by dt equals minus V over P times dP by dt, which is quite nice. And if you ever go into economics or microeconomics, you might see a similar looking formula for the elasticity of demand. But here it's for this expression. And now what are we given? We're given that V equals 600 centimeters cubed. We're given that the pressure equals 150 kilopascals. We're given that the change in pressure with respect to time is 20 kilopascals per minute. Well, this means that dV by dt equals 600 minus 600 over 150 times 20, which equals minus 4 times 20, which equals minus 80. So my change in volume with respect to time is minus 80 centimeters cubed per minute in the units. So the rate at which the volume is decreasing is 80 centimeters cubed per minute. I'll come back to the curve sketching in a later video. We now have a differential problem, and we're given a spherical egg, okay, with a radius of 12 millimeters, okay, and we have a measured error of 0.01 millimeters. So that means R equals 12 millimeters. dr by dt, dr could be up to 0.1 millimeters. And the question is, what's my possible error in volume? Well, volume equals 4/3 pi r squared, or r cubed, sorry. And it's asking what is the worst change in volume? Well, dV using differentials is I take the derivative of this expression, so V prime of R times dr. So the differential dV is 4 pi r squared times dr. My r is 12, my dr is 0.1. So dV equals 4 pi 12 squared times 0.1, which equals 144 times 4 pi times 0.1. 144 times 4 is 16, 17, 5, 57.6 pi. And that is the possible error in volume. And this would be millimeters cubed, because my radius is in millimeters and my error is in millimeters. And this is a classic differentials question. I give you a small change in radius, and I say use that to figure out what's the change in volume.